Welcome back, everyone. Today's explainer is a practical, no-nonsense masterclass built specifically for process engineers and technical minds. We're diving headfirst into the fascinating world of continuous polymer processing, and we're going to cover the whole shebang, from setting up your overarching tech flow to picking the absolute right hardware, and finally, troubleshooting those inevitable defects on the factory floor. So let's jump right into the playbook for mastering plastic extrusion.
Our agenda for today is broken down into 4 parts. 1. Technology overview. 2. Designing the extrusion process. 3. Equipment and dies. And 4. Troubleshooting defects.
Section 1. Technology Overview, the Extrusion Foundation.
Okay, so at its absolute core, extrusion is all about continuous production. Unlike cyclical methods like injection molding where you fill a mold, cool it, pop it open, and repeat, extrusion is a relentless, non-stop flow. We take thermoplastic or rubber materials, crank the heat way up past their glass transition and melting points, and forcefully push that melt through a shaping die. This is what lets us create literally infinite-length products. Think PVC pipes, long structural profiles, thin wrapping films, or even fiber optic cables. If we trace the material's journey from start to finish, it kicks off at the hopper, where solid raw polymer pellets are fed into the system. They drop down into a heated extruder barrel. Inside, there's a heavy rotating screw that simultaneously melts and drives that plastic forward. Once it's completely molten, it's forced through the die, taking on its final cross-sectional shape. But you can't just leave it like that. It immediately has to enter a cooling stage, which is usually a long water tank, to freeze that perfect shape in place. Finally, a set of pull rollers keeps the tension tight, constantly dragging the product toward a cutting or wind-up machine. It's just this beautifully synchronized system.
Section 2. Designing the process, building the tech flow. Now, let's put on our lead engineer hats. Your first real objective is actively designing the technological flow for a specific customized product. Building a successful line from scratch means mastering a 4-step life cycle. Step 1 is input and mixing, getting your base polymers, colorants, and additives perfectly blended. Step 2 is extruding and shaping, where all the thermal and mechanical heavy lifting happens. Step 3 is cooling or curing. This is super time sensitive, right? You have to lock in those dimensions before the hot plastic warps. And Step 4 is final processing, slicing that infinite extrusion into usable commercial lengths. Every single product requires its own bespoke tuning of these exact 4 steps.
A really brilliant example of these 4 steps in action is the continuous manufacturing of composite polymer rebar. Instead of just melting plastic pellets, this specific setup pulls continuous bundles of e-glass fiberglass straight through a liquid epoxy resin bath. Those resin-soaked fibers are then dragged through a sizing die to squeeze them into a tight cylinder and finally pulled through a long, high-temperature curing tube. It's a fantastic way to adapt basic extrusion principles to handle highly advanced composite materials. But here's the thing. As the process engineer, you aren't just sketching out flowcharts. You have to manage the real-world physics. Take that composite rebar. You have to perfectly balance 3 critical variables. First, the ratio of the curing agent in your epoxy. Second, the pulling speed of the fiberglass. If you pull too slow, your factory is just bleeding money. But if you pull too fast, the epoxy only cures on the outside, leaving a weak, gooey core. And third, the curing temperature. Heat it too much, and the epoxy will literally burn or evaporate locally. Heat it too little, and the rebar exits the machine completely soft. But when you nail those variables, when you run the experimental matrices and find the absolute perfect synergy of speed, heat, and chemistry, the results are staggering. Your finished composite rebar achieves a tensile strength 1.5 to 2 times higher than traditional steel. And get this, it's 5 times lighter. This is exactly why mastering process design is such a game changer. You are literally engineering a superior physical material just by how you control the extrusion environment.
Section 3. Equipment and dies, specifying the hardware. With our process flow locked in, the next objective is selecting the specific physical machinery to actually get the job done. Let's look right into the heart of a single screwed extruder. The raw material drops in from the hopper and gets caught in the deep flights of a heavy steel screw. As that screw turns, it conveys the material forward through a cylindrical barrel. Now, the barrel does have external heater bands, but a massive amount of the heat actually comes from mechanical shear. That's the intense friction of the plastic being physically squeezed and crushed by the geometry of the screw. That 1-2 punch of heat and pressure is what perfectly plasticizes the material by the time it reaches the end. As that molten plastic leaves the screw, it hits two crucial components that do very different but equally important jobs. First, it hits the filter screen and distributor plate. Now, obviously, these filter out unmelted impurities, but their hidden, arguably more vital engineering purpose is to create resistance. By restricting the flow, they build immense back pressure inside the barrel, which forces the polymer to mix and melt much more uniformly. Once past the screen, that highly pressurized, perfectly melted plastic slams into the shaping die. This is the ultimate sculptor. It gives the product its final physical identity, whether that's a flat sheet, a hollow tube, or a really complex window frame.
Now, depending on the material you're running, a standard single screw just might not cut it. Enter the planetary roller extruder. Picture a central main screw, entirely surrounded by multiple smaller satellite screws, all interlocking together like planetary gears in a transmission. As an engineer, you'd specify this kind of heavy-duty hardware when a specific material demands really aggressive, intensive mixing without excessive heat degradation. Making choices like this, matching the exact machine architecture to your polymer's specific thermal and shear limits, that's what separates a good engineer from a great one. Okay, so we've designed the process, and we've specified the perfect hardware. But here is the million-dollar question. What do you do when things inevitably go wrong on the floor? Because they will. What happens when your extruder speed is just slightly out of sync with your cooling tank, or your internal barrel pressure takes a sudden nosedive? Let's talk about manufacturing disasters.
Section 4. Troubleshooting defects. The Matrix.
This is your survival matrix for the three most notorious villains of the extrusion die. First up is melt fracture. If your product comes out looking highly distorted, wavy, or just completely irregular, you're dealing with an unstable melt flow. The engineering cause here? Usually it's excessive shear stress at the die walls, or a poorly designed die geometry that's creating dead zones where material gets stuck. Next is shark skin. It looks exactly like it sounds, a rough, matte, ridge texture on the surface. This happens right at the exit of the die. Basically, the core of the plastic is moving faster than the surface layer, which is dragging on the metal die wall. If your exit speed is too high, that surface layer literally tears as it leaves the metal. And finally, we have bamboo. If you just ignore shark skin and keep pushing your velocity, it progresses into bambooing. This is a severe, periodic tearing that leaves deep ridges looking exactly like the joints on a stalk of bamboo. It means you have a catastrophic velocity and thermal mismatch in your process that needs immediate fixing. Mastering extrusion is this incredible, delicate dance of chemistry, thermodynamics, and mechanical engineering. You now know how to lay out the continuous process flow from scratch. You know how to specify the internal hardware, from screws to dies, to maximize material properties. And most importantly, you know how to read a product's defects to instantly troubleshoot your machine parameters on the fly. So the only question left is, how are you going to apply this playbook to entirely optimize your next engineering project? Keep analyzing, keep innovating, and I'll catch you in the next explainer.